All right, welcome back. Chapter 6. In this chapter, we're going to be discussing matrices. Now, we saw a little bit of these matrices before break when we did systems of equations. Remember how we used our calculator to solve some of those systems that had 3 variables in it? Well, that was sort of a matrix in a way. So we're going to talk a lot more about them in this chapter, how we can add matrices together, multiply matrices together, and things like that. So what is a matrix? A matrix is a rectangular array of m horizontal rows and n vertical columns. The dimension of a matrix is denoted as m by n. So what a matrix is, it's basically a box. Let me kind of sketch one out. And this is how we sort of denote sort of the positions of the matrix. So first, let me give you an idea of what a matrix looks like. A matrix could just basically look like this. Just some numbers, yada, yada, yada. These numbers mean something, but, that's what a matrix looks like. And the more general format of a matrix is this. So this is a 3 by 3 matrix because it has 3 rows and 3 columns, okay? So that's kind of what this dimension thing was talking about before. Dimension of a matrix is denoted as m by n, the number of rows by the number of columns. So in general, though, we call this position A11 to signify that this is the first one here represents that it's in row 1, and the second one represents that it's in column 1. So the next position over would be A12 to signify that it is in row 1 and column 2. And the next one would be A13 for row 1 and column 3. And then it would keep going on and on and on, however big your matrix is, to A1 whatever, however many columns you end up having. And so the second row would start A21 to indicate the second row, first column. Then it'd be A22 to indicate the second row, second column, A23, and so on, right? And this pattern continues as well. So A31, A32, A33, and so on in all of these directions. So if I ask you what's the A11 position of the example matrix that I made here, it's 5. 5 is in the A11 position. It's the first row, first column. If I wanted to know the second row, third column, A23, second row, third column, that would be this 2 in that case. So this is just a general version of how we denote the positions of each number in the matrix. And you can see a little bit of that demonstrated there. Can I clear this so we can see it better? Yeah. So sometimes they use I and J as the general versions of it. Like that I represents the row number and J represents the column number. And we'll see a lot of that as well going forward. So if you see A, I, J, I and J just represent I row and J column. All right, so example 1, identify the dimensions. So remember, dimensions are row by column. So A has 2 rows and 3 columns. So this is a 2 by 3 matrix. We'll find 2, 1 entry of A in a second, but let's go ahead and finish the dimensions on all these. So B got 2 rows, 2 columns. It's a 2 by 2 matrix. C has 3 rows and 1 column, so it's 3 by 1. Sometimes people get mixed up there and they do 1 by 3 by accident, so it's very important that you remember to look for how many rows there are first, then how many columns there are second. D, there's only 1 row and there are 4 columns. This is a 1 by 4 matrix. So let's find the 2, 1 entry of A. So this is talking about the second row and the first column. So the second row is this one, and the first column is this one. So that is 4. The 2, 1 entry of A is 4. What's the 1, 2 entry of B? So 1, 2, that's the first row, second column. So first row, second column, that number is 0. That entry is 0. The 3, 1 entry of C, so that's the third row, first column. Third row, first column is 5. And then the 1, 1 entry of D, first row, first column, that's negative 0.2. Okay, so matrices are just, I mean, they signify something you'll figure out later on, but basically numbers organized into rows and columns. And it's important that we understand the positions of those numbers as well, because the positions of those numbers will be rather important later on. Another thing to make note of, column vector, and row vector. Column vector is basically a single column matrix like you see in C, and a row vector is a single row matrix like you see in D. So just single ones, right? Not like 2 by 2s or 2 by 3s, but only like 2 by 1s or 3 by 1s or 4 by 1s, or row vectors would be 1 by 3, 1 by 4, 1 by 5s. Just a single row or a single column. So keep that in mind, that we call those column vectors or row vectors. Decide whether w, x, y, and z are vectors. If so, give their dimensions. Also find the second coordinate of each vector. So w is a 1 by 5 matrix. This is a row vector because it's a single row. So we will note that. Okay, that could look a little better. It's been a while. X is a 3 by 1 matrix. It's a single column, so it is a column vector. We'll just pretend that this thing doesn't screw up my writing. Y is a 3 by 2 matrix. It is not a single row or a single column, so it is not one of those. And Z is both a single row and a single column because it's only one entry. So technically, Z is both row and column vector. All right. So because it is just a single row and it is just a single column, it's a 1 by 1 matrix, and that's totally okay. That's fine as well. You don't see it too much, but I guess technically it's still row and column vector. Equality of matrices. This is pretty self-explanatory. Two matrices are said to be equal only if all the entries in one matrix are the same as the corresponding matrix. So, for example, if I make a 2 by 2 matrix and this is a 2, 3, 0, -1 matrix, a matrix of equal value is exactly the same thing. 2, 3, 0, -1. It's pretty self-explanatory, but it's something I just obviously want to make sure it's clear to you guys. Addition of matrices. So this is where it gets kind of interesting. Now I've got some very mathy lingo going on up here, which I really hope you can take the time to try to read and understand. I'll do my best to explain it, but it's very simple what it says. It looks complicated, but it's extremely simple. So let A and B be matrices. A is the matrix Aij. So this is just, all this is saying is that our matrix has elements in it. We don't necessarily know how many rows or how many columns, but it's just some general matrix. It could be a 2 by 2 matrix. It could be a 3 by 2 matrix, whatever. It doesn't really matter. B is the matrix Bij. So this is only saying, it's basically saying the same thing that, as A. It's another matrix. However, what's important is that both of these are I and J, which means that whatever this I is and whatever that J is, that this is the same thing. So this is indicating that A and B have to have the same dimensions. So if this was a 2 by 3 matrix, this would also have to be a 2 by 3 matrix. Their I and their J have to be identical. The sum A plus B, so you add the first matrix with the second matrix, is defined as matrix C. So that's just saying it's a new matrix now. Cij. And this is just saying it's a new matrix. We call it C, but it has the same dimensions as before. So again, if A was a 2 by 3 and B was a 2 by 3, our new matrix will also be 2 by 3. But here's the most important part of all this. Cij equals Aij plus Bij. Now what that means is that you add the I jth element of A with the same ij element of B, and you get that equivalent element for C. So for example, you could have C11, which is the first row and first column of C, is the A11 value plus the B11 value. So again, all this says basically, if you look at the second bullet point, basically all this means is that you simply add the corresponding elements of each matrix together. So if this was matrix A, which is 2 by 2, as you can see, and this is matrix B, then matrix C is just simply adding up the corresponding elements. So if I want to know what C11 is, the number up here in the top corner, I'm going to add the A11 with the B11 value. So 2 plus 4 is 6. So C11, the first row, first column element in C, is 6. I just add up the first row, first column element of A with the first row, first column element of B. 2 plus 4 makes 6. And I do that for each corresponding element. So the second row, or first row, second column, 6 plus 7 is 13. So my first row, second column value in the matrix is 13 for C. 7 plus 5 makes 12, and -4 plus 1 makes -3. So that is matrix addition. It's very, very simple. I did want to take my time to explain this notation because when you go to college, you're going to see a lot more of this fancy notation. It looks very confusing and it looks very elaborate and confusing and complicated, but sometimes they mean very, very simple things, because all this said was essentially what we just did. We just took the corresponding elements and added them together. But it says it in a very mathy lingo. So it's important that we take time to try to understand that. Okay, so scalar multiplication of a matrix. Again, this is very simple. So let's read the mathy version of it, but then I'll explain what it means. If C is a number and A is a matrix, is an m by n matrix, so some dimension, doesn't really matter what dimension is, then the scalar multiple CA, so this is you basically taking a number and multiplying it to your matrix. As you can see in our example, we're taking a number like 2 and we're multiplying it to some random matrix. It's defined to be D, which is just indicating it's a new matrix. Again, Dij saying it's a new matrix. Where Dij, so an element in this new matrix is just C, which is our number that we're multiplying it by, times that same element in our original matrix. So if I want to know what the D11 element is, so this is if I call this matrix D right here, the D11 element is going to be the first row, first column element here in the top left corner. That's going to be whatever C is times my A11 value. So C in this case is 2. As you can see, that's the number I'm multiplying it by. So if I want to multiply these matrices together, I'm just going to multiply that C value with each corresponding element in this matrix. So 2 times 3 makes 6. Since 3 is the first row, first column number, that's going to be the first row, first column number in my new matrix. So 2 times 3 makes 6. It's kind of like distributing in a way. 2 times 9, that's going to give me my first row, second column. 2 times 9 is 18. 2 times 5, that's my first row, second column. Or no, second row, first column. 2 times 5 makes 10. And 2 times -4, second row, second column. 2 times -4 is -8. So my matrix D is this. It's basically distributing. But again, I do want to take the time to explain the weird math lingo sometimes. So, but yeah, pretty straightforward. You're just going to multiply your value, whatever that number that it is. In this case, it's 2, to all those elements inside that matrix. All right, so let's try some of these rules a little bit here. So let A equal that matrix, B equal that matrix, and C equal that matrix. Now notice they're all 3 by 2 matrices. Now that's important because the only way we can add matrices together is if they're the same dimensions. So if I'm going to do A plus B, let's do that first. I'm going to write these down. So 3, 2, 1, -1, and 0, 2. this matrix plus B matrix, which is 2, 1, 0, 2, -1, -3. Remember, all you do in adding is you add corresponding elements. So just take the 3, add it with the 2. 3 plus 2 is 5. 2 plus 1 makes 3. 1 plus 0 is 1. -1 plus 2 is 1. 0 plus -1 is -1. And 2 plus -3, that's 2 minus 3, so it's -1. So this is our matrix. This is the answer to number 1 here. Okay, I'm going to erase it. Good thing about videos is you can pause it if you wanted to. So if you need more time to look at it, you can, but I need this space. So find 2 times A. So this is 2 times A. A is the 3, 2, 1, -1, 0, 2 matrix. And again, when you're multiplying, basically you're just multiplying each element here, in this case by 2. So 2 times 3 is going to make 6. 2 times 2 is going to make 4. 2 times 1 is going to make 2. 2 times -1, -2. 2 times 0, and 2 times 2. And this is our answer for the second one. Find -1 times B. So -1 times B. So B is 2, 1, 0, 2, -1, -3. Same thing, just multiply -1 with each corresponding element. So 2 times -1 is going to be -2. -1 times 1 is -1. -1 times 0. -1 times 2. -1 times -1. And -1 times -3. So there you go. That's your answer for number 3. And number 4, finally. Find A, B, and C if A equals C. So A equals C means that this matrix, 3, 2, 1, -1, this is my A matrix, equal to C. We don't know what that value is. A to B, -1, 0, C. Remember, matrices are equal if their values are equivalently equal. So for A to equal this matrix C, then the first row, first column value has to be the same as this first row, first column, which means that this A value has to be the same thing as this, which is 3. So A's got to have to be 3. As you can see, the 2 equals the 2 already, so there's no real issue there. 1 has to equal this position, so 1 has to equal B, so B must be 1. You'll notice the -1s already are the same. The zeros here are already the same. And this 2 has to be the same as this value here. So 2 has to be C. So C is equal to 2. So that must be the A, B, and C value if, we're saying that A is equal to C. So that's your A, B, and C value in this matrix, given the fact that A was equal to C. All right. Interesting properties of matrices. A plus B is the same as B plus A. I'll let you kind of read these. I think it's pretty self-explanatory. These sort of properties. There's not very many properties of matrices. For example, you know how this is one we'll talk about later. But you know how you take in regular number sense, you can do 2 times 4, and it's the same thing as 4 times 2, right? 8 equals 8. But with matrices, this isn't one of these properties, by the way. This is one that we'll discuss later, but I wanted to point out the fact that matrices are quite a lot different than regular math. If I take a matrix, let's say that this is a 3 by 2 matrix or whatever, and I want to multiply it to matrix B, and let's say B is a 2 by 3 matrix. I can do that, but it will not be the same as if I did B times A. So if I did A times B, this matrix times this matrix, this one being first, this one being second, it would not be the same as this matrix as if it were the other way around. And we'll talk about that more. I don't know if it's going to be in this video or the next one, but it's very interesting that that property doesn't apply to matrices, and that's kind of fascinating. And I don't want you to think. I want you to realize that matrices are quite a bit different sometimes. I think we'll end this video here because I don't want it to be too long. The next video we'll talk about matrix multiplication, which is kind of what I was just a little bit referring to a second ago with A, B not equaling the same thing as B times A. So I'll see you in that one. All right. See you later. Bye.